All right, so now we're getting into the rest of Learning Target 3-2, and here are all of our learning goals. So we've been talking about covalent bonding. Now we're going to talk about the difference between polar and nonpolar covalent bonds. So we know that a molecule is one or more atoms that are linked together, and covalent bonds are between two nonmetals. Covalent bonds can be polar or nonpolar depending on the electronegativity difference and overall symmetry of the molecule. And we will talk about this in just a second. So a nonpolar covalent bond is when the molecules have an equal sharing of the electrons in the molecule. This is often a symmetrical molecule. Just like we have F2 here, everything is symmetrical. So symmetry, if we draw a line down the middle, does everything look the same on both sides? The answer here is yes. There's an equal sharing of the electrons in this bond here, and everything is symmetrical. So now, a polar covalent bond is when a molecule has an unequal share of electrons. So that means that the electrons spend more time closer to one atom than the other. An example of a polar molecule is HF, okay, just like this. Remember, F, fluorine, is one of our most electronegative elements, okay? In these polar molecules, we have an asymmetrical shape. That means if we draw a line down the middle, things do not look the same on either side of that line. And this causes an unequal sharing of the electron pair, that is the bond. Okay, so here on this diagram, we can see this is red, and this represents the fluorine. And over here is the hydrogen. The red means that the electrons are spending a lot of time over there. This side is super negative. Water molecules are actually polar. They have an unequal sharing of electrons. Pause the video for a second and jot down, what do you think is the most electronegative element in a water molecule? The answer is actually the oxygen. So if our electrons like to spend more time around our oxygen, then that means our electron is going to have a partial negative charge to it, because the negative charges are more attracted to it, meaning that the hydrogens will have a partial positive charge, where the electrons are away from most of the time. A sign that you might want to know is when we are showing a partial positive charge and a partial negative charge. We use these kind of weird looking symbols here with a little plus to say positive or a little minus to say minus. So you'll probably notice those on some of our future slides. Go ahead, pause the video, and draw the Lewis dot structure for Cl2. If this is my Lewis dot structure, is this molecule polar or nonpolar? If I draw that line right down the middle, things look the same on both sides, so this is going to be a nonpolar molecule. Now go ahead, pause the video, and draw the Lewis structure for phosphorus trihydride. This molecule has no way that we can draw a symmetrical line down the middle without splitting atoms in half, which can't happen. So this molecule is asymmetrical, not symmetrical, so it's going to be polar. And you can imagine that phosphorus, because we see a lone pair, we see two electrons here. You can imagine that phosphorus is going to hog those electrons. Now, we say something in science that says like dissolves like. This means polar substances will dissolve in other polar substances, and nonpolar will dissolve in nonpolar. This explains why water, which is polar, does not dissolve in oil, which is nonpolar. Now we'll talk about the difference between intra and intermolecular forces, which we like to call IMF. Now, intramolecular forces are attractive forces within a molecule. These are typically described as ionic, covalent, or metallic bonds. And in this case, we've been talking about covalent bonds. These are very strong forces because they hold a molecule together. Now, intermolecular forces are the attractive forces that happen between molecules to hold them together. These are all weak forces. Now we'll quickly talk about the different types of intermolecular forces. London dispersion force is the weakest type of IMF we're going to be talking about. It is the only type of IMF in nonpolar molecules. London dispersion forces result from temporary shifts in the density of electrons in electron clouds. So if this is our molecule, we have most of our electrons over here in our negative charge and less of our electrons here in our positive charge. This means that when we have two of the same molecules, or just any type of molecule, the negative and the positive will line up and form this little attraction to each other. This is present between all atoms and molecules. It's dominant, though, in nonpolar molecules, especially these guys. Another type of intermolecular force is called Dipole Dipole, and this is stronger than a London dispersion force. This is found in polar molecules. So this is very similar to London dispersion forces, but this is with polar molecules, and this is when the positive and the negative of different molecules attract each other and kind of hold those two molecules together. You can think of this if you're visualizing liquid water, and those molecules are kind of holding on to each other no matter where the water is going. They hold on to each other in little droplets. Lastly, we have something called hydrogen bonding, which is the strongest IMF found in polar molecules. This is when hydrogen is bonded to any of these molecules. Now go ahead and predict, does water experience stronger London dispersion forces or dipole dipole forces? Dipole dipole forces is our answer because water is polar, and this is experienced by polar molecules, which have an unequal share of electrons, like the oxygen, which is hogging all the negatives. They also experience hydrogen bonding, which happens between the H and the O, those partial negative and partial positive charges. Now, which of the following here has hydrogen bonding? Our answer is HF because we said hydrogen bonding can occur when an H is bonded to an F, a Cl, an S, an O, etc. Now, one last practice problem. Go ahead and draw an SiH4 molecule and then decide if the bonds are polar or nonpolar and determine the type of IMF present. So if this is our molecule, we see that it is nonpolar because we can draw a line through the middle and everything is the same on both sides. And we can assume that since this bond is nonpolar, it's going to experience London dispersion IMF. Nice job getting through this PowerPoint. I hope you took some great notes. You can go ahead and write down any questions you might have and want to ask in class tomorrow.